Hi, everybody. Welcome back. This is the chi-square hypothesis test lecture, and we're going to be using a very similar framework that we used for the z-test and the t-test hypothesis tests, but the chi-square is a little bit different. So let's get started. When we think about a population, we could think about dividing that population into groups. Examples of this could be age group, preference of a particular product, marital status, smoking status, health conditions, dietary habits, education level, region of residence, pet ownership, exercise frequency, employment status, and more. We can also call these groupings classifications of the population. In this lecture, we're going to explore a technique that determines if two classifications of a population are independent, in which case it would mean that they are unrelated, or dependent, in which case it would mean they are related. In the context of healthcare, here are some questions that we can ask. Are pet ownership and health outcomes, and by health outcomes, we can talk about stress level or exercise frequency or more, are they dependent or independent? So the two classifications in this problem are pet ownership and health outcomes. And we are going to compare the two classifications and see if there's a dependency, which means they would be related, or an independency, in which case they would be unrelated. So if they are related, if there's a dependency, we would expect owners with pets to perhaps have lower stress levels and maybe higher exercise frequency. But on the other hand, if they are independent, we wouldn't expect to see pet owners with any different health outcomes than those people who don't own pets. So that's what independence means. We wouldn't see any difference between the two classifications, pet ownership and health outcomes, for pet owners and non-pet owners. Here's another example. Our geographic region, either urban, suburban, or rural, and disease incidence, for example, the frequency of a particular disease like diabetes, hypertension, or respiratory issues, dependent or independent? Does where a person live, their geographic region, have a relationship with a particular disease? Dependent, there is a relationship, or independent, there is no relationship. So if they were dependent, we would expect to see significantly more incidence of diseases than any region, any other region. So perhaps respiratory issues, maybe we have a hypothesis that living in polluted areas increases respiratory issues, and that's more prevalent in cities. So maybe we would hypothesize that living in an urban area would increase respiratory disease. So if we have a dependency, we may see that. Whereas if we have independency, we would see no difference of disease prevalence across regions. We would see similar disease frequencies for people across all regions. Okay, and let's look at another example. Dietary habits. If you are a vegetarian or non-vegetarian and your body mass index, underweight, normal weight, overweight, or obese, are these two classifications dependent or independent? If they're dependent or related, data may show that vegetarians have a slightly lower BMI than non-vegetarians. I'm sorry, I said slightly. I meant to say significantly lower BMI than non-vegetarians. But if they are independent, both vegetarians and non-vegetarians would have similar BMI categories. Okay, so these are the kind of answers that we can ask ourselves with the chi-square test. So I'm going to show you first how we do the data collection. This hypothesis test is called the chi-square test of independence. And it's a statistical technique used to investigate whether the classifications of a population are related. In other words, are they dependent? We take a sample from the population and we separate the sample into different categories for each classification that we are testing from that population. So if we are testing pet ownership and stress level, we would look at the data in our sample and we would classify the data as either having a stress level of low, medium, or high, for example, if we use these three levels of stress. And we would classify pet ownership as owning a pet or not owning a pet. And we would put these numbers 40, 20, 30, 40, 20, and 30 into these categories based on their classification. The number of responses falling into the categories for each classification are recorded into a table. These are called observed frequencies. So an observed frequency is something that you observe in your sample. So in our sample, we are observing that there are 40 people in the sample who are pet owners with low stress level. And we could do that for the rest of these numbers as well. The whole table is called a contingency table. Every contingency table that we work with has a row classification and a column classifications. There are always two classifications. One will be row and one will be column. In this example, the column classification is pet ownership. And there are two categories, pet owner and non-pet owner. That's shown across the top here, pet owner and non-pet owner. And we have a row classification as well. It's the stress level, and there are three categories, low, medium, and high. Low, medium, and high. The totals for each row and column are also shown here. So while 40, oops, excuse me, 40 and 60 are, sorry, 40 and 20 are observed frequencies. The total or the sum of those two numbers is also shown on this table. 30 and 40 are observed frequencies, and the total of those two frequencies are also shown here, 70. And so we have totals here and here. Some observed frequencies that we could note from this contingency table are that the number of pet owners with high stress levels is 20. So we look at pet owners with high stress, and that value is 20. The number of non-pet owners with medium stress levels is 40. Non-pet owners with medium stress is 40. There's a total of 90 pet owners. So if I look at pet owners and I look at the total for that column, it's 90. And there are 60 people with low stress levels in this sample. So here's low stress, and both pet owners and non-pet owners make up a total of 60 people with low stress in this sample. So we can go on. There's lots of observed frequencies that we could note here, but those are just some of them. That's how we read the table. Now, observed frequencies are what we see in the sample. Expected frequencies are something else. Let's consider the fact that there are 60 people here with low stress levels. That's this row right here, 60 people. If we assume that stress level and pet ownership are independent, which means they have no relationship, how many of those 60 would you expect to be pet owners and non-pet owners? So if there's complete independence and there's no relationship and 60 people are low stress, then we would expect it to be split in half. We would expect about 30 people to be low stress and 30 to be low stress pet owners and 30 to be low stress non-pet owners to make up the 60. If there is complete independence, that's what we would expect. So I'm going to put a 30 here and a 30 here. These are what we would expect to occur if there is complete independence. Now I'm going to do that with the medium stress level as well. In the medium stress level category, we have 70 people in total. That's coming from here, and that's the sum of 30 and 40. But if we have complete independence between stress level and pet ownership, then how many of those 70 would you expect to be pet owners and non-pet owners? Well, splitting it in half, we would expect about half to be pet owners and half to not be pet owners, and that would make 35 and 35. I'm going to put those here and here. And let's do the last one. With 50 people, high stress, how many would we expect to be pet owners and non-pet owners, assuming independence? We would expect 25 to be pet owners and 25 of those people to not be pet owners. I'm going to put that here and here. Those numbers are special. They are called expected values. When we calculate expected values, we are assuming that the classifications are independent. So assuming no relationship at all, we can evenly say that the same number of, we'd have the same number of pet owners and non-pet owners in each of these categories. So those are expected values. Observed values are what you see in your sample. Expected values are the values you would get if you assumed independence. So what we see in a contingency table are always the observed values taken from the sample, exactly what we see in our sample. To test if our two classifications, pet ownership and stress level, are related, we want to compare the observed frequencies in the contingency table to the expected frequencies that we just calculated in the previous slide. Those are these expected frequencies. If a comparison is made and there's a big difference between the observed and the expected frequencies, a big difference indicates that there is a relationship. The expected frequencies, when we determine them, we do so assuming that there is no dependency between the two classifications. The comparison of the observed frequencies and the expected frequencies is calculated using a formula. So there is you would expect a difference being calculated here. O minus E is an observed frequency minus its expected frequency, and then it gets squared and divided by the expected frequency. O represents the observed frequency, E represents the expected frequency, and these are for each cell in the contingency table. And chi-square is symbolized by this capital X squared, and it is the result of adding up all of the observed minus expected over observed minus expected squared over expected frequencies across the whole table. So in the previous example, let me bring us back to it. There are 6 observed frequencies and 6 expected frequencies. And if we were to do this manually, we would apply those 6 observed and expected frequencies to this formula, and we would arrive at a chi-square value. But we're not going to be doing this manually. I am going to show you how to do this on your TI-84 calculators. So what does it mean when we get a value out of this formula? What does that value mean? It's a measure of the differences between O and E, between observed and expected. If the difference is small, meaning that it's close to zero, then we can conclude that the two classifications are independent. So if you look at what's happening up here, we're taking a difference. If that difference is not great, if it is a small difference, then this whole calculation is going to be small and chi-square will be small. So when we don't have a large difference, if chi-square is close to zero, then we make the conclusion that the two classifications are independent. So there O is close to E in that case. But if we do see, okay, let me just take a moment here. If observed and expected are exactly the same, which in the real world they usually never are, chi-square comes out to be zero. So if O is equal to E and you do the subtraction, you're going to get a zero. This whole calculation will come out to be zero and chi-square will be zero. So that's usually never the case, but at the minimum, chi-square is zero. It is never a negative number because there's a squaring part of this formula that ensures that even negative differences are going to become positive after they are squared. So the value is never, or chi-square is never going to be negative, only zero or greater. So any positive value of chi-squares indicates that there is some difference between the observed and expected frequencies, and the larger the chi-square value gets, the larger the difference between observed and expected frequencies. So the same reason why if there's a small difference, here we go again, sorry. Trying to erase without causing too much problem here. Okay, so if there is a small difference, this subtraction is going to be very small. But if there is a large difference, that subtraction is going to be pretty great. And eventually, when you do that over many cells that have big differences, you're going to get a larger chi-square value. So the larger chi-square, the larger the difference between the observed and expected frequencies. And just a reiteration that chi-square is a number that is never negative. It is always zero or more because of the squaring that goes on in the formula here. It's always going to ensure a negative difference is calculated and then or is evaluated as a positive number because you square negatives and they become positives. Okay, so a large chi-square, what it tends to tell us is that not only is there a difference between O and E, but there's a significant difference between O and E. A large chi-square indicates a significant relationship between the two classifications that you're measuring. So how big does it actually have to be? How large is large enough? Well, in order to say these two classifications are dependent, we need to conduct a hypothesis test to determine that. So in the same way that we did the z-test and the t-test, and we needed a difference between our sample statistic and our population mean, we needed that difference to be a significant difference. We're going to have the same issue here with chi-square. We need the difference between O and E to be a significant difference in order to say that they are definitely related. So we're going to go through the steps of a hypothesis test to do this. The distribution that we use is a distribution of every possible chi-square statistic in a sampling distribution, and it is called the sampling distribution of Pearson's chi-square test statistic. Now, it doesn't appear to look like a normal distribution. The chi-square distribution, a collection of every possible chi-square value, tends to look like it's skewed to the right, like this. And you could see how it starts at 0 and continues in getting positive in the right direction. So it begins with 0 and it only gets bigger as you move to the right. It is never negative, it's always 0 or greater. The smaller values are near 0 on the left side of the picture, and the larger values are on the right side of the picture. The graph of the chi-square distribution, it is not symmetric. It's skewed right. It extends infinitely to the right of 0. So like the distributions that we've seen so far, normal and the t-distribution, the chi-square distribution also extends infinitely. And this one only extends, though, to the right. Now, the chi-square distribution doesn't always appear in that particular, it doesn't always look like this picture. It takes on different appearances based on the number of rows and the number of columns in the contingency table. You see in this picture here different degrees of freedom, DF, which we saw with the t-distribution. Different degrees of freedom result in different looking chi-square distribution shapes. To calculate degrees of freedom for the chi-square distribution, we take the number of rows in our contingency table minus 1 multiplied by the number of columns in our contingency table minus 1. We don't include the row for totals or the column for totals when we are calculating degrees of freedom. If you take a look at what happens when the degrees of freedom increases, here's a DF of 20. It tends to appear like a normal distribution eventually. Okay, we are going to go through the whole steps of a hypothesis test for the chi-square distribution now. And in the end, we will make a conclusion, and then we will interpret that conclusion, interpret what it means based on the data. So we will determine whether or not we have a relationship between two classifications or we don't. So I'm going to go back to that example that we began with, pet ownership and stress level. A study was conducted at the 1% level of significance. We saw on our previous hypothesis test how knowing the level of significance is important and helps us make our conclusion. So here we're told that it's 1%. To determine if there was a relationship between pet ownership and stress level. So those are the two classifications. So 1 and 2. A random sample of 180 adults. That's the size of our sample. We could take note of that. Were asked their stress level and if they were pet owners. And we have this contingency table. Based on these results, can we conclude that there is a relationship between pet ownership and stress level at an alpha of 1%? So when we have this problem, next or side by side to a z-test and a t-test, there are definite differences here. In a z-test and a t-test, you are provided with a population mean, a sample mean, and some standard deviation, either the population or sample standard deviation. In the chi-square test, notice that you don't have a mean. The other thing that you see in a chi-square test that you don't see in the z-test or t-test is the contingency table. Data in a z-test or t-test, if raw data is provided, it's provided in a single list. In a chi-square test, data is provided in a table and organized by classifications. So that's how you know that you're working with the chi-square distribution and you're going to conduct a chi-square hypothesis test instead of a z-test or a t-test. So we're going to go through the same steps, but you'll notice that there are some differences here. The hypotheses are formulated without any statement about a population mean because there is no mean in the chi-square distribution. The population classifications pet ownership and stress level are independent. So that's the general formula for writing the null hypothesis. We state that we're talking about population classifications, not population means. Then we state what the two classifications are. Here they are, pet ownership and stress level. And then we state that they are independent. The null hypothesis always assumes that there is no relationship between the two classifications being measured. Now, usually in the z-test and t-test, I also ask that you symbolize your null and alternative hypotheses, but we don't have that in the chi-square hypothesis test. There are no symbols here. So you're going to go right into the alternative hypothesis. This is the opposite of the null. The population classifications, again, we're going to start with the phrase population classifications, followed by the two classifications, pet ownership and stress level, followed by the dependent relationship. Population classifications, pet ownership and stress level are dependent. And that's it for the null and alternative hypotheses in a chi-square test. It is very different. Notice there are no numbers here and there are no symbols that I'm asking of you. Okay, let's go on to identify the distribution. No population mean, no sample mean, no standard deviation of any kind. We have two classifications being provided, pet ownership and stress level. We're asked about there being a dependent or independent relationship. These are all indications that we are using the chi-square distribution in this hypothesis test. So when asked if you're using the t-distribution, the normal distribution, or the chi-square distribution, like you will be on the final, you will be asked this. Let me put it like this. You're going to choose the chi-square distribution. Okay, so our picture for the chi-square distribution, we're going to create a picture of a distribution that looks slightly skewed right. We're going to do the same kind of labeling that we did for the z-test and t-test. We're going to indicate the level of significance. We're going to shade in the critical region. We're going to label the conclusions across the top. So in a for a level of significance of 1%, we're going to shade in the topmost 1% of this curve. Now, in a chi-square test, it'll never be on the left. It'll always be on the right because there's only one direction for chi-square values. They start at 0 and they just get bigger. So the only indication of a relationship between two classifications is if chi-square is big enough, and large chi-square values are always going to occur on this side. Okay, so they are always going to be one-tailed tests on the right side, since a significant Pearson's chi-square test statistic will always be a positive number. Okay, notice I'm not labeling any means on the horizontal axis either. So this is the reject HO region. Eventually we are going to have a p-value. Any p-value that falls in this smaller than alpha, for example, is going to be significant. And if we have a significant p-value, it means we can reject the null hypothesis. It would also mean that our chi-square value falls inside this critical region. If the p-value is bigger than 1%, then we fail to reject the null hypothesis. It would mean our p-value is larger, it falls outside, okay, larger than alpha. And in that case, our chi-square test statistic will be in the non-critical region. This will give a result that is not considered to be significant. So those are the two ways that a test can end. We don't know until we look at the data. So let's keep going and see what we have here. The decision rule, how are we going to reject the null hypothesis? This is going to stay in line with a lot of what we've done already. We make the picture first, and then we state we will reject the null hypothesis and accept the alternative hypothesis at the level of significance of 1% if the p-value of the sample statistic is less than or equal to 0.01. So while we're using the same exact decision rule for all of these tests, recognize that the sample statistic in this problem is not the same as the sample statistic in a z-test or a t-test, where the sample statistic is x bar in a z-test or t-test. Here, the sample statistic represents the chi-square test statistic. So how do we find that chi-square test statistic? Then we go to step number 5 and we use our calculator. So we're going to jump to the calculator right now and analyze our sample data. But before we can do any analysis on the sample data, we have to enter it in the calculator. And it's different than putting data into a list because this is a table and it's arranged differently than a list of raw data values. So I'm going to share my screen and we are going to put the data into what we call a matrix on the calculator. So from your calculator's home screen, you're going to select the matrix function from on top. It's above the x to the negative 1 key. So second and matrix. And if you're opening this for the very first time, your matrices are empty. So what you're going to do is go over to Edit and hit Enter on the very first matrix, Matrix A. Okay, I have some data in here, but we are going to fix this. We're going to change the numbers up here. Instead of 2 by 4, we're going to change it into a 3 by 2 matrix. A 3 by 2 matrix is what the data in this problem gives us. It gives us stress levels, um, 3 of them, 3 rows, and it gives us pet ownership, 2 columns, 1, 2. So this is a 3 by 2 matrix. I want to make my matrix match the table that was provided to me in the problem. So once I have the 3 by 2 positioned like that, I'm going to fill it with the same values that were given to us in the table. So we're going to put in the numbers that the table provides, 40, 20, 30, and 40. Notice you could just write over a previous value that's in the table and it overwrites it and you got your new value now. 20 and 30. Okay. So the data's in the matrix. We are going to think about the matrix as the way we store table data, and we can use lists to store other types of linear raw data, but in tabular form, the matrix is what we're going to use. Now, also from this from the calculator, we are going to run the chi-square hypothesis test. So we're going to quit this matrix screen, second quit, and we're going to press stat, tests, and z-test and t-test that we are familiar with are at 1 and 2. The chi-square test is down a little bit further and it shows the chi-square symbol. And there it is. It's C for me. There's also another chi-square test beneath it, the chi-square goodness of fit test, GOF. We are not using that one. We're going to stay with the chi-square test. This is also known as the chi-square test of independence. So we hit enter. And here is where you specify where your matrix is. Now, if we keep using matrix A as the location where we put our data, we'll never need to change this. But if you happen to have an incorrect letter here that doesn't say A, but your matrix is A, you can put the correct letter in by doing this. Second, matrix, and with names highlighted, just press enter on A. Okay. Now, matrix B, for the expected values, the calculator uses this matrix to calculate its expected values and populates that expected values matrix. So we do not need to adjust this. Just make sure it's not the same as A. Okay, make sure these are two different matrices, but we are not going to be going into the expected frequencies and looking at them. The calculator needs it so it could do its calculations. So we're going to go down to calculate. We could hit draw, actually. Let's see what happens. Okay, that's the appearance of our chi-square this time. It is going to the right infinitely. It doesn't have that skewed right look because it doesn't have that hump in the beginning, but it's still the chi-square distribution. It's just the degrees of freedom are different here. So what you're seeing is a p-value of 0.0064. And also at the bottom here, you're told what the chi-square test statistic value is, 10.0952. You're going to need both of these numbers. You're going to take the chi-square test statistic and take it to 2 decimal places. So that becomes 10.10. And then the p-value you're taking to 4 places, 0.0064. Now this p-value is so small, it's practically not even visible on the screen. It's shading in an area that is nearly impossible to see. So we have a very small p-value. It is considered to be very significant. Now I could also get these two numbers by pressing, going through that test again, but hitting calculate instead of draw, and you will get the same answers. You just have to round the p-value. So going down to calculate, okay, you do see 10.0952, which we're going to round to 10.10, and the p-value 0.0064. So that's how we use the calculator to get the test statistic and the p-value. Okay, so you are going to be asked, what is the value of your sample statistic? That is its value, 10.10. You're going to be asked what its symbol is. It's chi-square. And you're going to be asked for the p-value, 0.0064. So you will be asked this on both the homework for the chi-square hypothesis test and the test question, the final exam test question. Okay, make our conclusion. Going back to our diagram, we said that the uppermost 1% was the significant region. And when we compare our p-value, 0.00, sorry here, 0.0064, and you compare it to 0.01, our p-value is smaller. So we do have a significant result. Our p-value is smaller than 0.01. Our chi-square test statistic falls inside the critical region. We could reject the null hypothesis. Okay, reject the null hypothesis, accept the alternative at alpha equal 1%. So going back to what our hypotheses were, when we reject the null hypothesis, we are rejecting that they are independent. And when we accept the alternative, we are accepting that they are dependent, rejecting HO and accepting HA. Okay, so next, in general, this is what it means when you reject the null hypothesis. Your p-value is smaller than alpha. You reject the null and accept the alternative. And what it means in terms of classifications is that you do have a significant relationship between your classifications. Significant relationship means they are dependent. Now, on the other hand, if you end up with a p-value that is bigger than alpha, you come to the conclusion to fail to reject the null hypothesis. That means you don't reject the null hypothesis, which is that there is no significant relationship between the population classifications, and when that happens, they are independent. So in this case, we fall over here. We have a significant p-value. We have a significant relationship. These two classifications are dependent. Okay, so let's answer our final question. Based on these results, can we conclude that there is a relationship between pet ownership and stress level? And since we've concluded that there is a significant relationship, we're going to say yes here. The sample data supports the claim that there is a statistically significant relationship between pet ownership and stress level. The two classifications are independent. And that's it. That's it for a chi-square test. I have one more example to show with you, but you can see how it takes, it's a little bit less numerical than the z-test and the t-test from our perspective, because there's no mean involved and there's no sample mean involved. The calculator does a lot of formulations, but conveniently, we are not going to involve ourselves with that. The calculator is going to take care of that for us. So let's look at another example. Type of diet and cholesterol level. A study was conducted at the 5% level of significance to determine if there was a relationship between diet type and cholesterol level in a particular population. A random sample of 180 adults was sampled, and the results are shown here. So you have a significance level, and you're going to be shown a table. That's an indication that you're going to conduct a hypothesis test of the chi-square style. So I see two different diet types. I have two row classifications, and I see 1, 2, 3 different cholesterol classifications. So my data is right here. The totals are not part of the data, and we would not be putting those into the matrix on our calculator, only the expected values that I boxed in here. Based on these results, can we conclude that there is a relationship between diet type and cholesterol level at 5%? So we jump right into writing our null and alternative hypotheses. The null hypothesis, the population classifications, this is how we always start. Diet type and cholesterol, so that changes from problem to problem. It's whatever the classifications are in the problem. And then we state that they are independent. HA, the population classifications, diet type, and cholesterol level are dependent. Null and alternative hypotheses. Next, you're going to decide on the distribution. There's no population mean, no sample mean, no standard deviation. The data provides you with two classifications. Oops, I don't mean to say pet ownership and stress level. Let's fix that. That is type of diet and cholesterol level. We're asked if there's an independent or dependent relationship. These are all flags, all indications that you are using the chi-square distribution in this hypothesis test. Okay, so you can either write chi-square like this, or you can use the symbol chi-square like that. And so that is the distribution. Okay, the picture of the distribution indicating the level of significance, the shaded critical region, and labeled conclusions. Let's always make a test on the right-hand side for the chi-square distribution. You could make it skewed right. The critical region is up here. The reject region is in the critical region, and the fail to reject region is everything else. Your decision rule tells you how you're going to reject the null hypothesis. So you will reject the null hypothesis and accept the alternative hypothesis at an alpha of 5% if the p-value of the sample statistic is less than or equal to 0.05, and realize in a chi-square test, the sample statistic is the chi-square test statistic. So we go to our calculator, we're going to put the data into a matrix, then we're going to run the chi-square test. Sorry, it says t-test there. It says the chi-square test is what we're going to run, and we're going to identify the symbol, the value, and the p-value of the sample statistic. So let's jump to the calculator and put in that data and run that test. Okay, so this is from before. Let me quit this screen, go back into the matrix menu, second matrix, go over to edit, and we are going to continue to use matrix A. We're just going to overwrite what was there before, matrix A. And our table is provided in the form, it's a 2 by 3 this time, because there are 2 rows and 3 columns. And the data is 30, 40, 20, 28, 42, and 20. Okay. Next, we're going to run the test, the chi-square test for independence. Let's quit this screen and press Stat, Test, go down to chi-square test, not the goodness of fit test underneath it, but chi-square test. Enter. Observed can stay at A. Expected can be B. We can either calculate or draw. If we calculate, we'll see our p-value, which is big, and our chi-square value is pretty small. So I'm curious, maybe I didn't put my numbers in right, but let me take a look at what this looks like when I draw it. Wow, okay. Now that's really an insignificant result. Let's make sure that my data in my matrix looks good. 30, 40, 20, 28, 42, 20. Okay, everything looks right. So I think that this data is just, the result is just really insignificant, not significant at all. So let me go back to this and pull out, I'm going to pull those 2 numbers out. 0.12 for the chi-square test statistic, 0.12, and 0.9428 for the p-value. Okay, it looks like I had an error in my slideshow. I had the wrong table. I gave you the wrong numbers, so I'm going to go back and fix those numbers. We're going to go back into the matrix, go into Edit, Matrix A, and the correct numbers here are 33. I will fix the slideshow. 33, 34, 23, and 25, 48, and 17. Okay, so now when we run the chi-square test, let's go down to draw. Okay, this is what I was expecting. The chi-square symbol is chi-square, and its value 4.39, 2 decimal places, and the p-value 0.1112. Okay, and we can get that same data by going to calculate as well. If you have an older calculator or your calculator's draw function is not working, you could just go to calculate and you can get that same information. So here are the correct values that I should have used the first time. I'm going to go back and fix this slideshow so you'll have access to the correct information if you choose to view the slideshow. And then when you plug this in and run chi-square test, you are going to see the chi-square test statistic value is for 4.39. That's coming from here. And its symbol is chi-square. Its p-value 0.1112 is coming from here. So since this is a 5, you're going to round the 1 next to it up to a 2. Okay, so if we wanted that p-value to be smaller than 5%, it's not. So let's do a comparison between the p-value and the level of significance. So going back to a picture, we have a level of significance of 5%, but the p-value is over 11%. So we are going to then fail to reject the null hypothesis. So in a chi-square test, failing to reject the null hypothesis is like accepting that they are independent, but rejecting the null hypothesis is saying that they are dependent. Okay, so we have a p-value that is bigger than 0.05. We are going to fail to reject the null hypothesis at alpha equal 5%. So in this case, we're dealing with this second scenario, a p-value that is bigger than alpha. There's no relationship, no significant relationship between the population classifications, and we conclude that they are independent. So now going back to the original question, based on these results, can we conclude that there's a relationship between diet type and cholesterol level? We're going to say no. The sample data does not support the claim that there is a statistically significant relationship between diet and cholesterol level. The two classifications are independent.